Good evening and welcome everyone to the November session of Astronomy on Tap, Leiden. And today we have two very exciting talks about European Space Agency's exoplanet missions, CHEOPS and PLATO. And so thank you all for joining us today. And before we go into the program, for those who are new here or would like a reminder, Astronomy on Tap is an initiative that started in 2013 in New York City. And currently there are more than 40 locations all over the world where Astronomy on Tap is happening, where we bring astronomers for everyone to share their works. And Astronomy on Tap Leiden is the first of its kind that started in Europe. And we have been working since 2017. And there has been already more than 3 years. And here are our social media channels. So we are on YouTube, of course, where you are watching us today. And we are also in Facebook, Twitter, and Instagram. Please tag us there and you can follow our updates and news about next events there as well. But also those who are not a big fan of social media, we also have a website and we also have a newsletter. So there you can find updates about our new upcoming events as well. For today's event, we're streaming here live in YouTube. So please, those who are with us, give us a shout out in the YouTube chat. Let us know where you're watching from. We really love to hear from you. And also after the talks, you can leave, also during the talks as well, you can leave questions for our speakers in the live chat during the talk. And when the talk is finished, as usual, our moderator will read the questions and our speakers will answer your questions from there directly. So before going to our today's program, we have some really relevant and exciting news from astronomy. So first of all, the good part of the news is that ESA's exoplanet mission Ariel, or the atmospheric remote sensing infrared exoplanet large survey mission, has moved from study to the implementation phase. So it's scheduled for launch in 2029. It's going to study the surface of more than 1,000 known exoplanets from different systems. So it's very exciting, and we're looking forward to this mission a lot. And along with it, there is sad news for astronomers. That is the very famous and prolific Arecibo Observatory is being decommissioned. It has been performing for more than 57 years right now, and it is being decommissioned because of some trouble in their cable structure. So there were two broken cable, and after further checking in the site, it has been known that it is very risky for even to repair, because the 900-ton structure can fall on even the people who will be repairing them. So they want to keep the instrumentation and the visitor system active, but we'll have to see what happens to this famous system. Just to give you some idea that we will always remember Arecibo for a lot of its contributions in science. So in 1974, the Arecibo Observatory was used to detect the first ever binary pulsars, for which the scientists who were involved got Nobel Prize in 1993. And also in 1981, Arecibo helped us to pierce through the cloud of Venus for the first time. And here you can see an image of the northern hemisphere of Venus that was also constructed using Arecibo, but in 2015, it's a later image of that. Also in 1982, Arecibo was used to image the first ever millisecond pulsar. And also in 1992, Arecibo helped us to detect the first ever exoplanet, that is the first ever planet that is outside of our solar system. These are only some of the few exciting discoveries that Arecibo helped us to do. So yes, we will always remember you. Thank you for your help in the scientific contribution. And now coming back to our tonight's program, we have two exciting talks from ESA's scientist, Kate Isaak, who will firstly tell us about CHEOPS, the first ever characterization of known exoplanets. And then we will have a regular quiz where you can participate in the question answers, and you can also win exciting prizes. And to take part in the quiz, we will share a link for the Google form that will be in the live chat that will be shared there, and you can fill in your answers from them. And after that, we'll have a short break, and then we will have our second talk by Anna Heras. It will be about ESA PLATO mission in quest of habitable works. And afterwards, we'll have, after each of the talk, we will have the question answer session. And at the end, we'll have the quiz answers, and we'll announce the winners, and then we'll conclude today's event. Now, for our first talk of the day, we have Kate Isaak, who is a scientist from the UK and based on the ESA estate. So it's the technical heart of European Space Agency in Noordwijk. She finished her PhD from University of Cambridge in the natural sciences, and that's where she started her fascination of working at the interface of astronomy and engineering, which she continues to do today. She's the project scientist of the CHEOPS mission, and today she is going to tell us more about what is this mission about and what is it gonna help us with in terms of science and more. And besides being an astrophysicist, Kate is also used to be a hang glider pilot and a beekeeper, but she is still struggling to combine these two in her identity, if I remember correctly. So yeah, that's all. And Kate, the stage is yours.
Thank you for that introduction and for the opportunity to talk here on virtually, I should say, on astronomy and TAP. As Lamim said, I'm Kate Isaak. I work virtually up the road at the European Space Agency's technical heart at ESTEC. And today I'm going to talk about CHEOPS, characterizing exoplanet satellite. Now, this is the work of many people. We're a small mission, but there's still many people involved. It's a collaboration between ESA and the Swiss Space Office and a total of 11 member states of ESA. And so I'm going to tell you about the satellite and what it's going to do and where we are. But before I start, I'll say a little bit about why we care about exoplanets. And the reason for this is we have one question, burning question: are we alone? Which is probably one of the most profound questions that we have as a civilization have. It's a question that has puzzled many of us over the centuries, and is one that we're starting now to answer today. So to address the question of whether we're alone, we need to find other planets, other worlds. And that is what an exoplanet is, a planet of a star that is outside our solar system, typically orbiting another host star, but not always the case. So the first exoplanet that was discovered orbiting a star like our own was discovered in 1995, 51 Peg B. This was a Jupiter-sized planet orbiting a Sun-like star with a period of about 4 and a bit days. Now, just to fix ideas, this compares with the orbital period of Mercury, which is of order of 88 days. So the planet is very, very close in, a big, gaseous, giant planet so close to the host star, challenged our understanding of planet formation. And this marked the start of the acceleration of exoplanet science from 1995 to the time we see here today. So how do we find exoplanets? 51 Peg B was found by a technique called radio velocity or Doppler spectroscopy, where the effect of the planet is measured by looking at the emission lines of the host star and monitoring the frequency or wavelength of the light from these spectral lines, and looking for the changes as the planet goes around the host star. These changes are the same as the Doppler effect that we see when an ambulance moves towards and away from us, with the star and the planet orbiting around a common center of mass. These very small changes are what enable us, in frequency, are what enable us to measure the mass of the exoplanets. A second technique is that of transit photometry, where we measure the change in light when a planet moves between us and the line of sight to the star. This small dip enables us to measure the size of the star. A third technique which is used is known as astrometry, and here we look for the changes in the position of the star as we measure as the planet moves around the host star. So here we can see that in each case, we're looking for small changes in what we measure from the host star. We're not actually detecting the planet itself, but we're looking for small changes in the star's properties, and from that we infer the presence of an exoplanet. The one technique that we have to find exoplanets where we are actually seeing the light from the exoplanet itself is direct imaging. And this is a technique which you've heard about in previous Astronomy on Tap talks, I believe, by Matthew Kenworthy. So the first measurements, or the first exoplanets, were found from the ground using the technique of radial velocity or Doppler spectroscopy, and then was closely followed by transit surveys. These soon moved to space, where we have the Corot mission, sorry, the Kepler mission, and the TESS mission, all of which were designed to survey different parts of the sky with a view to finding transiting exoplanets. So finding planets using the technique of transit photometry. So where are we today? Here we have a plot of the cumulative number of detections of exoplanets with time, the discovery year along the bottom of the plot. And here we can see a sort of hugely growing number of exoplanets to where we are now at over 4,000 known and confirmed exoplanets. We can see the large jumps in the numbers of exoplanets which have been discovered. First coming from Corot, which launched in 2006, then followed by Kepler, which launched in 2009, and the most recently launched satellite, survey satellite being TESS, which launched in 2018. The background image that I have behind this plot is an infographic by Martin Vargig showing the diversity of exoplanets that have been discovered by Kepler. This is an artist's impression, as we don't see the planets themselves, but it gives a nice feeling for the wide range of sizes and types of planets that we are discovering. So looking now a little bit on the statistics, the most commonly used method to find exoplanets is transit photometry, and this accounts for about 70% of the planets which are known to date. In close competition are the radial velocity technique and astrometry, and then we have microlensing and direct imaging with a few percent each. So, as I mentioned before, there are of order of 4,400 exoplanets which are confirmed and known to date, with several thousand waiting for confirmation. Of these, there are over 3,000 planetary systems, so systems in which these planets reside, and over 700 of these systems are multi-planet systems, so host stars around which more than one exoplanet is orbiting. So there's a great diversity in the exoplanet population that has been discovered to date. And here is a snapshot in which this can be visualized. In this plot, we see the semi-major axis, or the orbital distance of the planet from its host star, plotted against the planetary radius. And here we have the planets from our own solar system. So Venus, Earth, Neptune, Uranus, and other planets. Here we can see planets, sort of a bulk, grouping of planets, two populations here. We have a large number of planets which have been found, which have sizes between 0.1 and 0.3 radii of radius of Jupiter, and then we have a bunch of planets here which are around the size of Jupiter itself. And this population here is very close in. The Jupiters are very close in. We see that they're much closer in than that of the Earth. Unlike the Jupiter, which we see in our own solar system. And these we know as hot, we call hot Jupiters. We then have a second population, which I mentioned, which is the smaller planets. These are known as the super Earths to mini Neptunes. So they're planets between the size of Earth and Neptune. And again, this is a population, a type of planet, which we don't see in our own solar system. So new types of planets, unlike those seen in our own solar system. So we're moving now from a situation where we've been discovering large numbers of planets to one in which we need to characterize the planets that we have found. Moving from individual objects to looking at the demographics, and so looking at the large numbers of the planets that we have found, the systems in which they reside, and doing comparative exoplanetology. So by first step characterization, we can look at the mass of the planets and their radii, so their sizes. And here we have a plot of the mass and the radius of known exoplanets. Again, superposed are the planets from our own solar system. And we see here that we have a gap. This gap in planets is between Earth-sized planets and Neptune is an area where there are lots of planets which have been found to date. And this is a very interesting population that we wish to study. If we look here to what first step characterization enables us to do, with the mass, with an accurate mass and the size of a planet, we're able to determine the density of the planets, which is a first step characterization. With the accurate and precise measurements of the masses and sizes of planets, we're able to put constraints on the internal composition and structure of the planets. So start to constrain the models of the internal structure, what the planet is actually made of. And with these, we can start with large enough samples to look towards determining the formation and evolution of different types of planets. Here we have a plot where we have mass versus radius again, and superposed are planets, known planets, which have error bars on the mass and radius measurements of less than 30%. And here we can see underlying the plot a number of different models for the composition of the different planets, potential compositions. Iron, 50% iron, rock, 50% water and water. And we can see that in order to be able to constrain the internal composition and structure, we need to have a good measurement of the mass and the radius of the planet. And this is possible with bright stars. So this is where CHEOPS comes in, characterizing exoplanet satellite, as mentioned, a satellite, a mission in ESA's science program, and a collaboration between ESA and the Swiss Space Office through a mission consortium which is led by Willy Benz, who's at the University of Bern. What's special about CHEOPS and what's different about CHEOPS from previous exoplanet missions is that it's a dedicated follow-up mission. So we're studying known exoplanets that are orbiting bright stars. So we know when to point and where to point at the time at which a particular exoplanet transits. And we're looking at bright stars because it's with bright stars that we're able to determine the mass of the planets through the radial velocity technique. And so we have the combination of the mass and the radius of the planet. And there we start to do the first step characterization. So here we have some images of CHEOPS. CHEOPS is a small S-class mission in ESA's science program. Here you see a picture of the satellite at the satellite manufacturer site in Madrid. The satellite is about 1.5 by 1.5 by 1.5 meters to fix ideas on its size. It's small in size, small by ESA standards in cost and small in development time. The mission first started or kicked off at ESA at the end of 2012, and it launched at the end of last year. It's a mission which is very international. It's been tested. It's made its way around Europe. It has a good heritage, making its way around the different test sites of the European test facilities, here shown at the test center at ESTEC. Because it's a small mission, we were piggybacking with another satellite, or several satellites. In fact, we were a so-called secondary passenger. And here you can see CHEOPS during the integration at into the satellite fairing, which was done in Kourou, Europe's spaceport in French Guiana last November. So here we have CHEOPS, on top of which we have the three other additional CubeSats, and then the main passenger sitting on top. So how does CHEOPS work? We use the technique of transit photometry that I touched on very briefly. We make use of the fact that as a planet moves between us and the star, if we have alignment between the planet, the star, and ourselves, we see a small dip as the planet moves across the disk of the star. It blocks a small fraction of the light as it moves across. The amount of light that it blocks is proportional to the area of the planet, and so to the size of the planet. The bigger the planet for a fixed size star, the bigger the dip. So to fix ideas, Jupiter, if we were to observe Jupiter transiting the sun, we would see a 1% dip, which is 1,000 parts per million. In contrast, if we were to look to see the Earth transiting, we would see a contrast of 0.01%, which is then 100 parts per million. So we require ultra high precision photometry in order to be able to do transit photometry. By combining the transit depth that we measure with a knowledge of the size of the star, we're able to extract the size of the planet. And this is the parameter that we're interested in. What we can also do is to monitor the light from the star and how it changes as the planet orbits the star. So this is a so-called phase curve measurement, and what we're doing is not just measuring the light from the star itself, but also the reflected light from the day side of the planet. So in this way, we're able to infer properties of the day side of the exoplanet, whether it has clouds, for example, being a typical thing that we're interested in finding out. Here we have a light curve of a phase curve, and we can see the deep primary transit as the planet moves across the disk of the star, and then we have the small dip as the bright day side moves behind the star, the so-called secondary eclipse. There's a lot that we can learn from the light curves. We can determine the planet's size, orbital parameters, transit duration, and as I mentioned, we can say something about the albedo of the planet, so whether it has cloud, and from that whether it has clouds, what types of clouds it might have. And we can also, if we make these measurements at different wavelengths, we can also start to build up a spectrum, a transit spectrum. And with this, we can infer the presence of molecules in the atmospheres of exoplanets. Now, CHEOPS is a broadband, has a broadband instrument, so we measure light from 0.3 to 1.1 microns, all in one go. No spectroscopic capability, but that's what Ariel, the mission that you heard about in the introduction, will do. So we have one instrument on CHEOPS. It's a high precision light collector, and it's been designed in order to provide high precision, high cadence light curves. So it's been designed with stability in mind. We have baffle cover, which has been designed to keep dirt out of the telescope. And this is very important because this enables us to minimize, when we're actually in flight, it enables us to minimize the stray light that we get. So sort of reflections and contamination from other sources of light, sources other than the star that we're interested in observing. We have baffles which have been designed for exactly the same purpose. And these baffles sit in front of a telescope tube which houses the 30 centimeter effective diameter mirror, which sits approximately where my cursor is pointing. This mirror then feeds a detector. It's a CCD detector, which is cooled to a very modest temperature, minus 45 degrees centigrade, but it's held at a very steady temperature, which is the key importance. It's also a very low noise detector in order that we can measure very precise and stable light curves. So CHEOPS is orbiting the Earth. So it's in a 700-kilometer orbit, so-called sun synchronous. We stay at the same point relative to the sun in our orbit, in our 100-minute orbit, and we ride the so-called day-night terminator. And this we do in order to have the most stable orbit possible in terms of stray light. We want to minimize the stray light that we collect, or we potentially collect from the Earth, for example. By doing this, we're able to achieve the most precise and stable light curves. So the science of CHEOPS. CHEOPS is a follow-up mission, as I mentioned before, and we're studying known exoplanets orbiting the host stars across a wide range of different spectral types. We focus on stars which are relatively bright. The mission has been designed to observe stars with V-band magnitudes from 6 to 12. We are able to observe both brighter and fainter targets, but these are the limits on which the requirements are based. There are a number of science cases around which CHEOPS targets have been chosen. And these I've shown in this figure here. CHEOPS will improve the sizes of known exoplanets, and in doing so will improve the mass-radius relationship, which I talked about briefly earlier. It will determine very precisely features in the transits, in the light curves of transiting exoplanets. And for example, we'll look for exomoons or rings of these known exoplanets. It will study the atmospheres of exoplanets, primarily of hot Jupiters, because in order to be able to measure the phase curves, we need to have a reasonable size signal. And for that, we need to have the large planet, and the planet being reasonably close in. So we'll be able to study the atmospheres, that look for the presence of clouds, and study the dynamics, the energetics of the atmospheres of hot Jupiters. CHEOPS is a follow-up mission, but we will also be able to search for planets, primarily using the technique of transit time variation. So here what we're doing is to monitor the transits very carefully. And by looking for small changes in the timing of the transit, so the so-called mid-transit time, we're able to infer the presence of other previously unknown planets. We will also use CHEOPS to study stellar activity. We have high cadence, so we're able to take measurements every minute. And with this, we're able to build up very detailed light curves to monitor the activity of stars and look to see how this impacts on the planets that we're studying themselves. So the science program of CHEOPS is defined by the science team of the mission consortium, which is behind CHEOPS. So 11 member states of ESA, led by Switzerland. But on top of that, there is a so-called guest observers program. And this accounts for 20% of the observing time on CHEOPS, and this is open to the community as a whole. Anyone can apply for time on CHEOPS, and in fact, the set call for proposals for the second year of CHEOPS closes tomorrow lunchtime, so it's quite a busy time for us just now. So CHEOPS launched last year, December. It was quite an exciting time, launching from Europe's spaceport in Kourou. It was due to launch actually on the 17th of December, not the 18th, but there was an abort of the launch 1.5 hours before the launch actually took place. So we had a déjà vu, which was an interesting experience, getting up at a god and awful hour of the morning and returning to watch the launch, or to experience the launch, I should say. Here's some very nice pictures of the launch, taken very close to the launch, to the rocket itself. It's a so-called Soyuz rocket. It's over 40 meters high. I was sitting way away from the actual launch, so about more than 20 kilometers. And as I was helping with the commentary for the launch, I actually didn't see very much at all, but I was able to feel and hear the sound of the launch, which was extremely impressive. And of course, see the photographs taken afterwards, one of which is this beautiful trail of the launch itself. So over the Christmas holidays, just before the Christmas holidays, we finished the so-called early operations phase, and CHEOPS and the whole team had a good break over the Christmas vacation. Coming back at the beginning of January, we started the commissioning, where we started to exercise the instrument and exercise the satellite itself. And about 3 weeks after starting the so-called commissioning, we took the cover off the instrument and we saw our first light. And this is one of the first images taken by CHEOPS. And the immediate reaction is, what an ugly point spread function. Is this really what we're expecting? And yes, I can confirm it is. It's in fact a perfectly blurred image, deliberately blurred, in order that we spread the light over multiple pixels, and so increase the stability of the CHEOPS instrument. We have this trefoil-like shape because of the way in which the mirror is actually supported. So it's a known feature, shall we say, which doesn't impact on the quality of the photometry that we're able to get. So here we have the target star sitting in the middle of the image, and we have other stars in the field that we see as these ghost-like shadows. In the top right, we can see here the impact of the orbit as the spacecraft goes round the Earth, orbits the Earth. We continue to point at the star, the central star, our target star, but the spacecraft rolls around the pointing axis, and so the field stars rotate around also, as we can see here. So this is our first transit. It's a transit light curve of Kelt 11b. This is of a hot Jupiter orbiting a star, a local, reasonably local star, I should say. And here we can see a beautiful, we could see a beautiful transit light curve. So we can see the dip of the transit, the duration of which is of order of 8 hours. And this is a measurement that would not be so easy to make from the ground. It's a bright star that we're looking at, but the duration makes it quite challenging to measure to observe from the ground. The error bar that we see here is 0.1%. So we can see how the precision with which we're able to measure the light curve quite nicely. So from the first transit, we move to the first science paper that came out from CHEOPS. And this is of observations that were made of WASP 189. Here we see the star and the planet orbiting around its host star. It's the planet itself is a Jupiter, approximately Jupiter-sized, orbiting in a period of around 2.7 days. The star is very hot and quite large and rapidly spinning, and this has an impact on the transit light curve itself, which we can see in the shape of the curve. Here we see both the occultation or secondary eclipse light curve and also the transit. So the occultation, when the planet moves behind the star, and the transit, when the planet blocks a fraction of the light from the star itself. So where are we now? We're 9 months into operations. We've got just over 2.75 years remaining. There are many interesting results that are to come, many observations to be made, and importantly, there are opportunities for all to use CHEOPS. So to finish up, CHEOPS is a small mission, but their contributions which have come from many, and here in this slide, the many teams, or photos of the many teams that have been involved in CHEOPS. The science team, the instrument team, teams at ESA, at ESTEC, and during the launch, teams that were responsible for integration and launch at the spaceport in Kourou. So CHEOPS is not just about science, but it's about art too. Exoplanets inspire inspire us as citizens at very many different levels. And here we have a number of examples of the types of art that have come out of CHEOPS. And with that, I thank you for your attention to the talk and take any questions that come.
Great, thank you very much, Kate, for that interesting talk. Amazing what a small mission can do already in less than 1 year of operations, right? We do have a few questions already from the YouTube, so I'll just read them out for you. The first one is from Abratej. And the question is, do you ever get any false positives in finding exoplanets? And how do you determine if it's a false positive or not?
CHEOPS, yes, there are lots of false positives, in fact, and but CHEOPS is not a mission that is specifically looking for exoplanets. We're not searching for exoplanets, but we're following up on known exoplanets. So this is not something that we have to deal with.
So sort of related to that, do you only follow up confirmed exoplanets? Or
Absolutely. In general, yes. I mean, this is what we're doing. The targets that are chosen for observation by CHEOPS are known exoplanets. And so indeed, we follow up. We may discover, as I mentioned, new exoplanets, but that's not the thrust of the mission. It's a follow-up mission to characterize known exoplanets, to start to characterize known exoplanets.
Okay, thanks. The second question from Tuan is, using transit photometry, do you only measure the apparent size of the planet? And how do you measure the actual size of the planet with transit photometry?
What we're doing is we measure the size of the planet relative to its host star. So it's a relative measurement. So the dip the dip that we measure represents the fraction of light which is blocked by the planet. So we need to know the radius or the size of the star. And when we have that, we're able to combine that with the transit measurement, the depth, and from that we can get the size of the star. Now I should say that the size of the star, the size of the planet will differ at different wavelengths, and so this is something which is that Ariel will capitalize on, and by looking at the differences in the apparent size of the planet as a function of wavelength, we can build up a spectrum, a transit spectrum of the planet. But that's not what CHEOPS will do. We measure the broadband white light size of the planet.
Thanks. A final question from Savan is if you have any citizen science projects for exoplanet hunting, or perhaps you know of any.
We don't have one ourselves, because as I said, we're a follow-up mission. We'll probably observe around a few hundred planets over the lifetime of the mission. So we're not searching for planets, rather characterizing them. But there was a citizen science program based around Kepler data. I don't know if they're doing something similar with TESS, but Anna might be able to comment on whether there'll be something similar done for PLATO in the future. But there's nothing like that planned for CHEOPS, unfortunately. But there will still be exciting science to come out of the mission.
Great. And if I may ask just one last question here. You mentioned the 20% of the time is open time. I was just wondering if that's only for exoplanet studies, or I have no idea about the specs or what it could else be useful for otherwise, but is it just exoplanets or anything?
That's a very good question. We have we are measuring, we have the capability to do high precision, high cadence, so measurements to make measurements every minute. So this is a capability which is useful across different fields in astronomy. Our faint target limit is around 12th, 13th magnitude, so we can't go super faint, but our light curves have various different uses in other fields of astronomy. I mean, stellar science is one particular example, and also studies of trans-Neptunian objects, for example, looking at occultations of stars by TNOs is something that CHEOPS is capable of doing. So any science which makes use of the high precision, high cadence photometry can be done with CHEOPS.
Cool. Well, thank you very much for that talk. If you will see in the YouTube, if people have further questions, perhaps they can leave them there, and Kate may be able to answer them. So thank you very much.
Sure. Thank you.
All right. So I hope you can all find the URL in the YouTube chat soon. And if you can't, you can also just retype this URL. So the first game we're going to play tonight is called Fill in the Blanks. Can you match the answer with the correct sentence? So the first question is about the Hubble Space Telescope. The Hubble Space Telescope already spent ... years in orbit. So the four answers are here below. It's either 15, 11,000, 28,000, or 30.5. So you will have to match the different numbers to the ABCD. So the first question is the Hubble Space Telescope already spent ... years in orbit. And number 2 orbits the Earth ... times per day. Number 3 weighs ... kilograms. And number 4 travels at a speed of ... kilometer per hour. So I'll give you a second to fill that one out. Then we'll go to the next question. At the International Space Station. So the answers are, or the options are 18, 2, 50, and 6. And question number 1, up to ... ships can dock at any time. Question number 2, astronauts have to exercise ... hours every day. Number 3, more than ... computers control all the systems. And number 4, there have been individuals from ... different countries. All right, next question. How many ... have been discovered? So the options are 1350, 163, 0, and 1458. So number 1, Neptune-like exoplanets. Number 2, gas giant exoplanets. Number 3, exomoons. And number 4, terrestrial exoplanets. So match the numbers with the 1, 2, 3, 4. All right, then the next question. How long did the voyage to the destination take? So the options here are 5 months, 5 years, 6.7 years, or 10 years. So number 1, Juno took ... to reach Jupiter. Number 2, Rosetta took ... to reach the comet, with a very complicated name I'm not going to pronounce. Then number 3, Venus Express took ... to reach Venus. And number 4, Cassini-Huygens took ... to reach Saturn. All right. And then the final question of the first game, what causes the color of these planets? So number 1, the bluish color of Uranus is caused by, so the options here are silicate rocks, sulfuric acid, methane, and iron oxide. So 1, the bluish color of Uranus is caused by ... Number 2, the reddish color of Mars is caused by. Number 3, the yellowish white color of Venus is caused by. And number 4, the gray color of Mercury is caused by. All right, I hope you all did great in this game. Then we'll go on to the second game called Earth versus Space. Which image is from space and which one is from Earth? So I will show you 10 questions and with 2 pictures, and every time you have to guess which image is from space. So the very first one, A or B, which one is from space? Then question number 2. Again, A or B. Those look very similar, so this is a hard one. And number 3. And number 4. Number 5. Number 6. Number 7. Number 8. Number 9. And finally, number 10. And then in case everyone did really well, of course, we have a tiebreaker question. So the tiebreaker question of this month is, how far is the most distant human-made object from Earth in kilometers? So fill out your tiebreaker question to be able to win the game in case of a tie. And we're not going to go through the games again, but you can replay the games yourself in the YouTube. Just don't forget to click again on live when you're done to be able to follow the second talk. And check your email to see the amount of points that you received. You'll be able to still fill in the Google form and submit it until our break is over. So we're going to go on a little break now, and we'll see you back in a few moments for another talk.
And we are back after our short break. I hope you all enjoyed the games put together by our games team. These really fun games about informations about space missions and images from space and Earth. And now it's time for the second talk of the day. And our second speaker of the day is Heras, who will tell us about the ESA PLATO mission. And before she starts, let me tell you a little bit about Heras and her work. She did her PhD from the University of Barcelona, and currently she is working as an astronomer at the European Space Agency at the Stake, Netherlands office. After doing her PhD, she worked for a while at the National Oceanic and Atmospheric Administration in the United States, and then she came back to the Netherlands to work at the ESA Stake office as a research fellow. Then she worked for a while at the ESA office in Madrid, but then she came back to the Netherlands ESA office to work as a deputy project scientist for the Herschel Space Observatory. And ever since then, she worked in different missions in ESA Stake, and in recent years, she started working in the fascinating field of exoplanets. She initially worked on the study phase of the CHEOPS mission, and currently she's working as the project scientist for the PLATO mission. And in her talk today, she's going to tell us more about her work at the PLATO mission. And apart from when she is doing science, she is enjoying her multinational family who are from the Netherlands, Spain, and Greece. In their family, they enjoy all the traditions and festivities from these three countries. So it must be really colorful. So with that, I will give the screen to Anna, please.
Thank you very much for this introduction. I'm going to talk indeed about the PLATO mission. We are not still so advanced as the CHEOPS mission, where we already seen the launch and we've seen indeed wonderful data. So PLATO is still in development, but well, I think it's quite interesting to see what the mission will be doing and also how it is designed. So first, what is PLATO? So before we continue, the PLATO mission is an ESA mission, and its role will be to discover and characterize new exoplanets. So in this case, it's not following up exoplanets that we know, but indeed to discover also new ones, and exoplanets that are orbiting up to the habitable zone of bright sun-like stars. PLATO will also be using the transit method. It's a transit survey, but in addition, it will combine its measurements with ground-based observations in order to determine the characteristics of the planets. PLATO is the third medium-class mission in the ESA Cosmic Vision program, and the launch date is planned for 2026. Okay, what do we need PLATO? I mean, why after very successful missions like Kepler, like Corot, like TESS, we still need another transit survey? Well, we have a number of confirmed exoplanets, indeed more than 4,300. And of these exoplanets, we know some things, but we don't know so much as we would like to. We have, for example, so if we have here the number of exoplanets for which we have the radius, there's the large number of them. In the diagram, you can see that the faintest stars are going to the right, and most of the transit exoplanets have been discovered around faint stars because they are coming from the Kepler mission, and the Kepler mission was focusing on these particular ones. However, if we really want to know the mass of the exoplanet, and if you want also to characterize the atmosphere, so you need bright stars. And this is why for those planets for which we know the mass, then you see that we have a number which is closer in this area of the bright stars. When you look at the stars that are overlapping, so then there's of course a smaller number. But if you really want to look into exoplanets which are small, so that are up to 2 Earth radii or 5 Earth masses, then actually we only have 64 small planets that we have the radius and we have also the mass measurement. And this is not so much because, as we saw before, also in Kate's talk, exoplanets are very diverse. Therefore, it's clear that if we want to increase this number, we need to observe bright stars. And then these bright stars will allow us also to do measurements on the ground or do measurements with other facilities in order to characterize the exoplanet better. Okay, so this brings me to the next point, which is precision. Indeed, we have this number of exoplanets, small planets, for which we have radius and mass, but even for those, the precision of the values is not always what we really need to understand their composition. So here is the same plot as was shown in the previous talk, and it's a radius versus mass display, and the lines symbolize what model would be looking into, will represent when a planet is only iron, 50% iron, rock, or fully water, an ocean planet. And as you can see here, so already with the error bars that we have for the best objects, which is less than 1/3 of the 64 that we said before, so then it's sometimes very difficult to distinguish between the different compositions. And especially when you go to the smaller exoplanets where the Earth and Venus are, then you can see that indeed it's not only that the error bars are big, but also there are no values. And here I represented what the PLATO uncertainty will be for a star of magnitude 10. And the idea is that PLATO will be able to determine the radius of the exoplanet of the size of the Earth with a 3% accuracy, and the accuracy of the mass with 10%. So then this will improve indeed a lot these diagrams and will teach us a lot what these planets are made of. Then to continue understanding and explaining what PLATO will be doing, I want to explain also the concept of habitable zone. The habitable zone is defined as that region around the star where water can be in liquid form on the surface of the planet. Therefore, it depends, of course, of how close the exoplanet is from the star. And then in some sun-like stars, it's at the distance approximately like the Earth, clearly. If we go to smaller stars that are colder, so the habitable zone is much closer. So then it would be even in regions that are closer to the distance that Mercury is now. But this is indeed for stars that are smaller and colder than the Sun. Clearly, the habitable zone is one way to represent what the concept of habitability, but we cannot forget that there can also be habitable moons, for example, we imagine that it could be in the moons of Europa around Jupiter. But at least in order to have a framework where to discuss habitability, this is the way that we normally define the habitable zone. Okay, just to understand what we know about the exoplanets in the habitable zone, here I took this very nice representation for the Planetary Habitability Laboratory, where they show all the exoplanets that we know with the distance from the Earth and also their sizes in comparison, as you can see, with the sizes of the exoplanets, of the planets of the solar system. And from these exoplanets, it's fascinating that we have found them, but of course we want to know much more. So how many of these exoplanets are around stars that are similar to the Sun? So actually only these three. All the other ones that we have in this catalog, and are the ones that we know, are around stars that are smaller than the Sun. They're much smaller. They're called M dwarfs. They are sometimes between half or 1/10 of the size of the Sun. And that's why these three exoplanets that we have here are around stars that are similar. But how many of these exoplanets do we know the radius and mass? And actually for none of them. So we only have either the mass or we know the radius. And as we've shown before, if we want to start characterizing an exoplanet and to know about its composition, about if it has a magnetic field, about if it has plate tectonics, about if it has an atmosphere, we first need to know the radius and mass. And that's why this is where PLATO comes in. So PLATO will allow us to fill this diagram that now is so empty, because it will really specialize in looking for potential habitable exoplanets orbiting solar-like stars, and for which we can indeed determine the radius and the mass. But PLATO will not be only looking at the transits, looking for transits of exoplanets, but it will be so precise that actually will tell us a lot about the stellar properties. And as well, I think was a question before also about what we really measure with the transit method. We measure indeed the relative size of the exoplanet with respect to the star. When we measure the mass of the exoplanet, we also measure with respect to the mass of the star. Therefore, we only know the exoplanet as good as we know the stellar radius and the stellar mass. In addition, if we want to determine and see how planets evolve in time, we also need to know the age of the planetary system very precisely. And to determine ages is very difficult in astronomy. And we do it, but there are large uncertainties. And then indeed, it depends on the model that one applies. Therefore, we need to improve in that area and to be able to determine the ages of the mean sequence stars much better. And for this, we are going to use with PLATO the technique which is called asteroseismology. And asteroseismology is indeed a method that looks into the light curves in the frequency space, and then analyzes and interprets the oscillations of stars. Stars oscillate This is a little bit like an earthquake type of oscillation, and it depends on what the star is made of. It depends on the different layers that it has. It depends on the age of the star, of size, that these oscillations are different frequencies, different amplitudes. So by analyzing these oscillations, we will be able to determine very accurately what is the stellar radius, the mass and the age. And then for this, we will be able to derive precisely the property of the exoplanet. Okay, so we already seen what is the main goal of PLATO, what are the requirements. I hope that is clear that indeed we need to detect and characterize exoplanets with high precision and around bright stars. But the question is that, yeah, bright stars are not so many. I mean, we know that, of course, I mean, they are what they are. They are distributed uniformly in the sky. It means that it's difficult to observe them all together at the same time, especially when you want to detect a transit. Why is that also? Because the transit probability is not so high. I mean, especially it depends of the distance of the exoplanet from the star, and it can be 10%, but this is for the exoplanets that are very close to the star, up to 0.5%, and this is indeed for exoplanets that are at the same distance as the Earth from the Sun. And if you can imagine, if you have only 0.5% of probability of detect an exoplanet around a bright star, it means that you need at least, well, 200 stars, or sometimes, well, it can be conditions where this probability is a little bit smaller, but normally it's between 100 and 200 that you need to observe one transit of a small planet around the star like the Sun that is at the same distance of the Earth. So how do we solve this? I mean, we really need a large field of view because indeed the stars are distributed uniformly on the sky, but at the same time, we need to observe them with a lot of precision. And if one wants to build one telescope that does all this, it's very complex, and also it needs a size and a structure that maybe doesn't fit into, or is very difficult to fit into the constraints of the mass and the cost and the size that the mission has to be, and it has to fit also in the launcher. So that's why in the particular case of PLATO, the scientists who proposed the mission came to the idea to have a multi-telescope approach. So PLATO has 24 cameras, has 2 more for very bright stars, which are here at the top. And these 24 cameras are such that they are oriented not exactly in the same direction. So they overlap partly, but not fully. And this is the sky field of view that we get with PLATO. And the numbers here indicate the areas that are covered by this number of cameras. So 6 number of cameras cover the blue area, 12 the green, 18 the red, and 24 the white. And of course, the more cameras you have, obviously you can collect more light from these stars, and you can go to weaker, fainter stars in order to get the signal to noise ratios, or as we say in exoplanets, noise to signal ratios that you need in order to detect the exoplanet. Therefore, it's quite interesting. You can imagine this is also a very big field of view, and then it's 48 degrees by 48 degrees. If you look at the sky at night, so then this field of view will be sort of 1/4 of the sky that you can see. So you can imagine the PLATO field of view projected is quite impressive. And then this can be done within the constraints of the mission and on the satellite and on the launcher, because we have this system of overlapping some cameras and others not, such that we can cover the maximum surface possible. Okay, how many of these sky fields we will be observing? We are going to do, in principle, 2, because we need to detect Earth-like planets that are have 1 year period, and then we would like to detect at least 2 transits, and the mission nominal lifetime is 4 years. And well, this is the nominal. We expect to get extensions and to be longer observing these fields. But in principle, we have 2 sky fields that will allow us to observe more than 250 1,000 stars with magnitude brighter than 30, and of those, 15,000 will have a precision which is 50 part per million in 1 hour, which will allow us to do asteroseismology and will allow us indeed to detect the smaller planets, which are the Earth-like planets around Sun-like stars at 1 AU in the habitable zone. Okay, so this is just a movie of how the satellite looks like. It will be launched with the solar panels folded, and the solar panels will open. Just to give you an idea, so the height of the satellite is around 3.5 meters, so it's quite tall, and the extension of the solar arrays is more than 8 meters. This will be quite an impressive spacecraft when we have it in the test area. I hope that we can indeed send pictures, because it will be quite beautiful. And then with the 26 cameras, it's also going to be quite nice to see. Here also you see in the part of the spacecraft where the solar arrays are, the high gain antenna, which will be used to communicate to Earth. And in principle, well, the mass is 2,000 kilos, and there will be well, operationally, it can work for 6.5 years, but the consumables are going up to 8 years. So we hope that indeed we will get the extension to be observing for more than 8 years. Okay, the payload. So then, well, this is just a detail of one of the 26 cameras that PLATO will carry. The aperture of the cameras is 12 centimeters. And they will be working in the visible. It's actually, in this case, is indeed white light. Well, the cameras will have a cadence of 25 seconds, which allow us to see the transit in very good detail. And then for the bright star cameras, the other two, then the cadence will be 2.5 seconds. And then here on the right side, I wanted to show you one of the CCDs of the cameras. Well, this for us, we are very proud of this. Is for us indeed, well, an engineering marvel, I would say, because this is one of the 104 CCDs that PLATO will carry. There will be 4 of these devices per camera, and they are a 4K by 4K pixel array. They are, well, when they come all together, and they will be the biggest CCD camera ever built, which will have 0.7 square meter camera. So then you can imagine quite a huge compared to the ones we are used to in our mobile telephones or in our home cameras. And then, of course, this is necessary to have a very big field of view to observe as many bright stars as possible. And well, we have it already. Actually, the flight model of the CCDs are already in at ESTEC, and they are, we are very happy that this development has been very successful, and we are now going to integrate the CCDs in the cameras. Okay, the PLATO, the orbit that will follow is around the second Lagrangian point. So here you have a scheme. The second Lagrangian point is 1.5 million kilometers, so 100 of the distance between the Sun and the Earth. And it will go in this place because we need a very good stability. We need very good stability thermally, so as far as the Earth as possible, but still, of course, that can be in a place where an orbit is stable and also can send the commands in the right timing. And it has also to be an orbit that doesn't have eclipses or doesn't have shadows, because we need to have a very unperturbed observation during 2, 3, or 4 years, whatever it takes to detect these very long period exoplanets. Well, I hope that I have convinced you that PLATO will really provide a big contribution to our understanding and knowledge of the diversity of exoplanets, of how planets form, of how planets evolve. PLATO is indeed an effort that is sustained by more than 700 scientists that are distributed in 22 countries, in universities and institutes of 22 countries. And that is also built by tens of companies all over Europe. So indeed, it's a really huge effort of many, many people that, well, we all want indeed to address and to go to find an answer to the main question, to one of the most fundamental questions we have, which is how unique is Earth in the universe. So, well, thank you very much for your attention, and I finish here.
Great, thank you, Anna, for that interesting talk. We have a couple of questions already. The first one, the answer may have been on one of your slides, but the question from Roger is, other than Proxima Centauri b, how close are the other terrestrial planets in terms of light years from our sun? Yeah, so then actually then this is the closest one indeed. So then it's a range between indeed the 4 light years. One of the others, sun-like, is around 10 light years, but we don't have the radius and mass, but indeed is also relatively close. But the Kepler ones are quite far because they are more than 100 light years. So then, we can of course show it in order so people can have, let me see, so this. So then the last ones, they are even 1,000. You see this quite far. So, but of course, the ones that are mostly interested in are the ones that are, around maximum 300 light years or so. So then this at least can give us the opportunity to detect the masses and also to do a spectroscopy. With 1,000 light years, it may still be possible, but it's much more difficult then because, of course, then the star is fainter. And it's one of the reasons, one of the reasons why these exoplanets don't have masses is because indeed the stars were too faint. But okay, so then you see it's a distribution. We are not going, there are other methods that will go much farther, actually. With the transit and the radial velocity method, we don't get that far. But if you, for example, go into microlensing, and there then indeed you can detect exoplanets, you don't get very well their characteristics, but microlensing is very, very good to give you an idea of the distribution of exoplanets in the galaxy. And then you can go much farther. And so then we can have a better overview. But then at the cost that we cannot characterize the planets so well. So that's why, the closer they are, the better we can characterize them. And then the other ones are, a little bit more difficult. Great, thanks. A second question from Andrew is, can Plato differentiate multiple transits around occurring at the same time?
Multiple transits occurring at the same time. I don't know if I understand this question. If it's...
Yeah, I'm not sure if it means at the same time around the same star or around...
Well, Plato will detect multiple transits, indeed. If two transits overlap, then of course it's very difficult because, you can maybe disentangle something. If they don't have the same period, because maybe they overlap, but then of course they don't have the same period and they don't overlap anymore. So I think that probably the question means multiple transits, and indeed it will be able to detect as many transits as possible according to the precision. And for each star, the precision is different because, as you see, we don't have a uniform field of view. So depending on the star is on the field of view, we will have one precision or the other. And we will be able to detect the smaller exoplanets.
Okay, I think I just saw the clarification. There was overlapping transits, which you answered.
Yeah, well, it's normally they don't have. It's very beautiful, the transits of TRAPPIST, for example, because there are overlapping transits, and then you see the difference that there are two exoplanets because they are not exactly the same size. So you always see either if they are not exactly the same size, and when they overlap, so then you see a transit shape that is slightly different. And of course, they are normally not exactly the same period either because of they are not at the same distance. So then, in the end, you can see that you can disentangle them. You can see this. Therefore, there are different ways to do it. But the example of TRAPPIST is very beautiful to see overlapping transits indeed.
Great, thanks. And if I can ask, you You focus a lot on also the astroseismology of characterizing the star systems themselves. Are there differences in the pulsations of solar type stars and less massive stars? Is one easier to characterize than the other?
Yeah, actually, our knowledge of the oscillation of stars ends normally with in the lower end of K stars, put it this way. So because for M stars, we will not be able to detect oscillations with PLATO probably, and they are not still well studied because it's very, very difficult for these stars. I mean, the frequencies and the amplitude of the oscillations are, are very difficult to determine. So that's why our goal is indeed to detect oscillations in main sequence stars. And normally the larger the star, the easier it is to detect the oscillation. When you go to red giants, the amplitudes are really big. And so for the M type of stars, let's put it this way, it will be the next challenge. And then maybe, I mean, if PLATO, we manage to get very, very good light course, we can do some work there. But in principle also it's very difficult to model them. I mean, because they have different structure, they are not so, well, it's a challenge. It's a challenge, let's put it this way, for the M stars. But for the, down up to the mid-K stars, we will be able to detect oscillations.
K is just after our sun, right? I'm just trying to remember my star basics.
Yeah, the K. So the K are just the ones before the M, yes. So, yes.
Yeah, sorry, I just thought I'd clarify that. Okay, great. Thank you very much for a nice talk. If there are any further questions, just leave them in the chat and Anna might be able to answer them there. Otherwise, we move on back to Anik for the answers of the quiz.
Okay, I hope everyone found their points in the email. It was actually really, really close. So I'm very excited at how well everyone did the game. So for the first game, the Hubble Space Telescope, it already spent 30.5 years in orbit. It was launched actually in 1990. So that's already quite some time ago. And it orbits the Earth 15 times per day, which also means that if you're an astronaut on the ISS, you will see the sun set and the sun rise 15 times per day, which I think probably must be very magical. And it's pretty heavy, weighing 11,000 kilograms, and it travels very, very fast at a speed of 28,000 kilometers per hour. Then the next question, at the International Space Station, up to 5 ships can dock at any time. And actually, currently, it's very busy at the space station. There's 5 ships docked, so it's almost full capacity. And apparently, even astronauts have to sleep within the spaceship itself because there's not enough space in the station. Then astronauts have to exercise 2 hours a day, and they have to do this to retain their muscle mass, because of course, because of the gravity, all your muscles are weakening. There is more than 50 computers that control all the systems, and there have been individuals from 18 different countries to the ISS. How many exoplanets have been discovered? So the Neptune-like is the most of all, it's 1,458. Then the gas giant exoplanets, 1,350. And these are fairly easy, or not easy, but easier than the others to discover because they're fairly large and massive. But we have not discovered yet any exomoons, so the correct answer was 0. There are some candidates of exomoons, but none of them are confirmed yet. But this will be very revolutionary when we actually have the discovery of an exomoon. And the terrestrial exoplanets, so the exoplanets that look like Earth, there's 163 cases confirmed at the moment. Then how long did the voyage to the destination take? So Juno took 5 years to reach Jupiter. Jupiter is the biggest planet in our solar system, and it's quite far away, so it took 5 years. But it took even longer to reach the Rosetta comet. It took 10 years, and that's mainly due because of the complicated orbit of the comet. The way to Venus took a little bit less long. It took to Venus Express 5 months. Venus is a little bit closer to the Earth. And Cassini-Huygens took 6.7 years to reach Saturn. Saturn is a little bit further out than Jupiter. Then what causes the color of these planets? So the bluish color of Uranus is caused by methane. Methane actually absorbs red light and re-emits blue light. So that makes Uranus appear blue. Then the reddish color of Mars is caused by iron oxide. And actually the most common form of iron oxide is rust. So when you look at Mars, you can see that it also looks very rusty, a rusty planet. And the yellow-whitish color of Venus is caused by sulfuric acid. And on Venus, it's actually very thick clouds of the sulfuric acid. And these clouds are so thick that you cannot even see the actual surface of Venus, which is fairly rocky. And then finally, for Mercury, the gray color is caused by some silicate rocks. All right, then for the second game, for the first question, the correct answer was B. This is a radio image of a galaxy. You can see the nice spiral arms here. And on the left, we actually have a tornado image on Earth in the satellite in infrared. Then question 2. In photo A, you see the surface of Mars taken by a Mars rover, and on B, the desert on Earth. Then question number 3, the correct answer is B. And here we see a simulation of the large-scale structure of the universe. So this is a really, really big part of the universe. And in all these tiny dots you see could be galaxies forming. And you see a large dark matter distribution. And on the left, you see neurons, so brain cells on Earth. Then number 4. Left is the correct answer, number A. It's the International Space Station. So maybe what could have given it away is maybe the half-floating laptop and gear here all strapped to the walls. There's not really any up or down, but maybe you were thrown off a little bit by this man who appears to be sitting, but I think he's probably hooked onto something. And on the right, we see a submarine. Then number 5, A is the Rosetta's Comet, and B are just mountains on Earth. So I hope you all recognized the well-known mountains. Then number 6, the correct answer was B. These are aurora on Jupiter, taken in UV. And I think they're like as pretty as the aurora that we see on Earth. They're way, way stronger too. Then 7, correct answer was A. These are galaxies in the Hubble Deep Field. And this is the deepest image we have in optical of the universe. So all these tiny dots you see here are galaxies. And on the right, those were bacteria. So this is a picture taken under a microscope. Then number 8, on the left, we see an image of Venus in the UV. And on the right, we see an image of Earth in the infrared. And you see that Venus also has thick bands of clouds, which is why it looks kind of similar to the Earth in the UV. And then number 9, the correct answer was B. The dunes on Mars is what we see here. This is a picture of the Mars Reconnaissance Orbiter of NASA. And here on the left, you see sand dunes on Earth. And this is also taken by a satellite, this picture. And then the final question, number 10, correct answer is A. This is the Bubble Nebula, NGC 7635. And this Bubble Nebula can be found in the constellation of Cassiopeia. And on the right, I think you probably all recognize this as a beautiful soap bubble bursting. And then the tiebreaker question. So how far is the most distant human-made object from Earth in kilometers? So the correct answer is 22.5 billion kilometers. And this is really, really far away. It's the spacecraft Voyager 1, who's already on its way for 43 years now. So we can see here in this picture Voyager 1 in the red, and it's almost about to leave the sphere of influence of our sun. It's already past our furthest planets and will one day also go into the Oort cloud. So the winners, the non-astronomers and the astronomers. So for the non-astronomers, we had a tie between Pennsylvania and Kochhuis, both with 26 points out of the 30, so really well done. And on the tiebreaker question, Pennsylvania won. So congratulations. And then for the astronomers, we again had a tie between Mick Eda and Kira Ike. And there they had 28 points, both of them, but on a tiebreaker question, Mick Eda won. So congratulations to all, and everyone did really well. We will send you an email to send you your gift. And then we're gonna go back to Lamin for closing off.
So we are almost at the end of our today's event. So congratulations again to the winners. I mean, yeah, 28 and 26, that's excellent points. And I hope you all enjoyed the exciting and interesting talks and really fun games. And if you enjoyed the event and you'd like to check out more of such Astronomy on Tap online events, please, you can go check it out on the website astronomyontap.org. And with that, actually, today's event was the last event for the year 2020 for Astronomy on Tap Leiden. We take a break for holidays in December. And our next event is on 25th of January in 2021. So yeah, the year 2020 has been a bit of, it's been pretty bizarre for many reasons for all of us. And for Astronomy on Tap Leiden, we also had these online and offline sessions throughout the year, depending on the situation. So a big thank you for all our audiences who have been with us throughout all of this. And yeah, we hope that you will also join us in the year 2021. And of course, we'd like to take this opportunity to thank our speakers. Thank you very much for being accommodating and doing all these things for the online event. And of course, in a regular situation, we'd like to give you this token of thanks at the spot, but we cannot do that now. However, we'll make sure that these classes find their way to you in good time. And yeah, last but not the least, of course, a big thank you and shout out to the entire team of Astronomy on Tap Leiden. So here today, we are only a few of us online, but of course, the whole thing cannot run smoothly without all of your help and support and efforts. So thank you all, and thank you to all our audience, and we hope to see you in January. We wish you a very good evening today and a very, very happy holidays. Bye.